Hey, there we are. We're live. Hello, everyone. Welcome to 2015. Oh my gosh. I am Mr. Bray, as you can see, and we are in the Bray Cave. But I hope you had a great vacation, wonderful little respite. And I thought what I'd do is go through a little bit of Unit 9 since you have the unit exam coming up. And it's been like almost 2 weeks since you thought about moles and molar masses, because I know that's the top of your thoughts. So I got some questions here ready to go on the iPad. I got coffee ready to go. Number one, dad. Sorry to all your dads out there. They're just not as good as me, evidently, because I have the mug to prove it. But anyway, so I thought I'd go through some of the stuff on Unit 9. We'll see how long it takes. If you have questions, feel free to shout a tweet over to at WindsorChem. It'll show up, and I'll see if I can answer it if you're watching it live. If not, come see me in school, and I'll answer it as best I can. So Unit 9 was all about the mole. Oh, before I go there, I also have to apologize. If this is grainy, if the audio is splotchy, if it doesn't match up, I apologize. I had to make kind of a makeshift network to get this all to work. So I'm hoping it's coming through at a decent speed, but hey, we'll see. Who knows? So anyway, Unit 9 was all about the mole and chemical quantities. So we said a mole is a certain number of things, just like a dozen of something is 12. And it doesn't matter what it is, 12 things is a dozen of those things, and a dozen of those things is always 12. Well, one mole is 6.02 times 10 to the 23rd things. And that number was 602 sectillion. But if you have 6.02 times 10 to the 23rd things, you have a mole. Now, we got a little weird when we talked about atoms versus molecules and all that kind of stuff. So let me actually, I didn't think about doing this, but let me move here on the iPad. Oh, way too far. Let's go here. Okay, so that'll work. All right, let me switch over and we'll take a look at the difference between an atom and a molecule, because technically it makes a difference. So when it comes down to it, there are it's been a little while since I wrote. Sorry, let's clean this up. There's no second takes in live TV. Okay, so there's atoms and molecules, right? And those can mean different things depending on what you're dealing with. But a particle is one of those two. A particle could be an atom, a particle could be a molecule. It's however the thing exists. So if we, let's switch ink colors. And if we kind of think about it this way, like if we say Ne, well, Ne is an atom. So in that case, a particle is an atom, because a molecule has to be two or more different atoms, and they can be the same element, but different atoms bonded together. So in that case, a particle is an atom. But if I were to look at something like CO2, now that exists as a molecule. So in that case, it'd be 6.02 times 10 to the 23rd molecules of CO2 in a mole. There's more than the atoms, because there's 3 atoms for every 1 molecule. If I were to look at oxygen, right, that's O2, oxygen gas. Let's loop that around. So again, that's a molecule. That's 2 different atoms, even though they're the same element, 2 different atoms that are bonded together. And as a result, it's a molecule. So whether something exists as when we say 6.02 times 10 to the, whoa, what am I doing? There we go. There we go. 6.02 times 10 to the 23rd particles. It could be an atom. It could be a molecule. It depends on how that thing exists. If it exists as a molecule, then you have 6.02 times 10 to the 23rd molecules. There would be more atoms. If it exists as a single atom, you'd have 6.02 times 10 to the 23rd atoms. But that's what a mole was all about. So from there, we talked about the idea, and I'm switching up here a little bit. We talked about molar mass. Now, molar mass is how much 1 mole of something weighs. So if you took 6.02 times 10 to the 23rd pence and put them on a scale, that'd be the molar mass of pens. If you took 6.02 times 10 to the 23rd iPads and put them on a scale, that would be the molar mass of an iPad. Well, for atoms, it's the same thing. But we can find that molar mass by looking at the periodic table. So let's just take a quick peek here. I don't know why it's making it difficult, at the periodic table. So when we look here, that mass that we saw before, that's the molar mass. So in the case of like magnesium here, if we round this to the nearest whole number, it'd be 24. So the mass of magnesium would be 24 grams per mole. If we scoot over and look at something like oxygen, well, here's oxygen, we can round that to 16. Now, the thing that you got to keep in mind is that if you took the 1 mole of oxygen atoms, see, this is where that molecule and atom thing comes in. If you took 1 mole of oxygen atoms, it weighs 16 grams. But 1 mole of oxygen gas, which is O2, would be 32 grams, 16 times 2. Sweet. I know, we're kind of warming up the brain a little bit. It's been a little while. Let's remind you who number 1 is. So anyway, what I thought I'd do here is I got a couple problems where we were dealing with molar mass and calculating molar mass and a couple other things. So let's just dive right into those. So we'll head over to the iPad, and there we go. So this first question asks, what's the molar mass of calcium phosphate? And the formula, it's a little tricky the way I gave you the formula, but I think it'll work. It is Ca3, PO42. So if I were to write that differently, right, I can't do subscripts with the notability here as easy as I want to. So it'd be like Ca3 PO4 2. So if I want to do the molar mass, I just have to look up the mass for each of these. But if I think my way through it, it's going to be the mass of Ca times 3, because there's 3 of them. And then I'm going to add that to, well, let's see, there's 2 PO4s, which means there's 2 P's. So the mass of phosphorus times 2 plus the mass of oxygen. Now this one's a little tricky because it's 2 times 4. So it'd be 8, right? I mean, if you wanted, you could also do Ca times 3 plus P plus O times 4, right? We talked about this. And then multiply that whole thing by 2, right? You could do that if you want. It's just, I think it's a little bit easier to make mistakes that way, but hey, do whatever you want to do. So when I look up these masses, going to the nearest whole number, of course I didn't bring a calculator. Why would I bring a calculator? That would make sense. Calcium to the nearest whole number is 40. So I'm going to have 40 times 3, okay, plus phosphorus. When I look up phosphorus, that is 31. So we'll do 31 times 2, plus I know oxygen is 16 times 8. So when I do all that math out, let's see, 40 times 3 is 120, plus 31 times 2 is 62, plus 16 times 8. That one I'm going to have to cheat and do a calculator, is 128. So add that to 120. And add that to 62, and I'm coming up with, hopefully, because I'm doing it quick, 310. So it'd be 310 grams per mole, right? So that's what that one's all about. So that kind of showed you and reminded you about how distribution works and all those fun little gadgets. So let's take a look at something else I have here. This wants to know what's the mass of 3.68 moles of nitrogen gas. Well, okay, this one's a little different because you have to remember some of the unit cancellation that we did. So first off, nitrogen gas is N2. And if I think about that, nitrogen weighs 14. If you look it up on your periodic table, multiplied by 2 is going to be 28. So what does that tell me? That tells me that 1 mole of N2 is equal to 28 grams of N2. And the question, let's switch ink here, started me with 3.68 moles of N2, right? Remember this from unit, this would be homework page, I think 3 is where this came into play. So I need to get this into mass. I need to get this into grams. So that's where my unit conversion comes in. And I already know that moles of N2 have to go on bottom to cancel. And I know that 1 mole of N2, I guess I can get rid of the S, 1 mole of N2 is 28 grams of N2. So that cancels my N2 because they're opposite each other, right? This is like it's over 1. And that leaves me with 3.68 times 28, which I'm coming up with 103.04. And my units would just be grams of N2. But that was all homework page 3, I think, on the Unit 9 packet. Excuse me for a second. So yeah, you can look back on that and see. I can't remember. Let's see if I can pull it up real quick here on the computer and see which video it was on Google Drive and on YouTube. Boop, 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 Unit 9. So this would have been 9.3 on either the YouTube channel or Google Drive. This was all 9.3, and then go back for unit conversions. Go back to, like, I think it's 3.2 or 3.4. It's back in Unit 3. But anyway, let's keep going here. So here's another one. This wants to know what volume, and I'll switch ink again here. In liters, would 94.7 grams of argon gas occupy at STP? Well, what we said is the 1 mole of something always weighs a different mass depending on what it is, but 1 mole of any gas is always equal to 22.4 liters at STP. So I'm going to have to do a little bit of work here because they actually started me with grams. Now I know that 1 mole of, in this case, argon, which is Ar. If I look that up on the periodic table, rounded to the nearest whole number, that's going to be 40 grams of Ar. So I can put this all together and I can say, okay, let's start with the 94.7 grams of Ar that they gave me. And then we'll say, all right, I need to get it into liters. So the grams of Ar is going to have to go. And right here, I know 40 grams of Ar is 1 mole of Ar. So that gets rid of my grams, leaves me with moles. But again, I need liters. So we'll switch ink again. And I've used that. But, oh, here, I still know moles, right? So 1 mole of Ar is 22.4 liters of Ar, because no matter what the gas is, 1 mole of that gas will always occupy 22.4 liters. So that gets rid of my moles, leaves me with liters, and now I know I have the right answer. Effectively, what I have left is 94.7 times 1 times 22.4 liters of argon, all divided by, 40, there we go, times 1. So let's see, when I do that math out, what am I going to get here? Let's clear that out. 94.7 times 1 times 22.4, I'm getting 2,121.28, divided by 40 times 1 is 53 we'll call it 032, and my units are liters of argon, LAR. Right? Cool. So with this here, let me come back and talk to you here for a second. Stop. And go. So with these problems, the way this works is you have to use unit conversion, which is back in Unit 3. And like I say, I want to say it might be video 3.2, I think 3.2, to solve it. And the unit conversions that you're going to use for this are that 1 mole of something always equals its mass off the periodic table. Okay. 1 mole of something also always equals 22.4 liters if it's a gas at STP, which we'll talk more about STP later. But for now, it's just 1 mole of a gas is always 22.4 liters. You want to know that number. And also 1 mole of of anything is 6.02 times 10 to the 23rd particles. And if you get a problem like that, they're probably just going to have you show the setup, because sometimes it can be a little funky with the calculator and getting calculations of that. So excellent. So let me clean. Oh, that's not what I want. Let me clean this up a little bit. Where we went from there, we scooted, and that was like homework 4, 5, and 6, I think, maybe 3, 4, 5, and 6. I can't totally remember now. But it was like the mole and mass, and then it was the mole and Avogadro's number, the mole and volume, and then mixed mole problems was all of those. So you can go back and look and see what those were all about. But from there, we got into percent composition, which, let me take a look on Drive here. Percent composition was 9.4. So you can either check out in Google Drive, you got 9.4, or in the YouTube channel, video 9.4 is also going to help you with percent composition. But the formula for that is right on the back of your reference tables, and it's part divided by whole times 100 is percent composition by mass. So I have a couple problems here showing you that. Let's take a look at those. This first one wants to know, what is the percent composition by mass of oxygen in sodium carbonate? Now, kind of the mean thing I did here. Normally, I would give you a formula. So let's do that. Sodium carbonate is Na2CO3, because I'm not necessarily testing to see if you know how to get from a name to a formula in this case. I could certainly do that later, but that's not what I'm shooting for here. So let's see, to get the mass of this, and well, it'd be Na times 2, and I'm going to add that to carbon, and there's just one carbon, and then I'm going to add that to, whoa, let's make that a little neater, to oxygen times 3, because there's 3 oxygens. So when I substitute in my numbers, sodium has a mass of 23, so it's going to be 23 times 2 plus carbon is 12, plus oxygen is 16 times 3. So when I bring up my handy dandy calculator of science, which is probably not going to last too much longer because my batteries are dying, that's going to be 46 plus 12 plus 16 times 3 is, I know I should do it in my head, but I'm lazy, 48. And when I add all that together, there's 12, I come up with 106. So to do percent composition, it's the mass of the part. And in this case, they want to know what is the percent composition of oxygen. So it'd be the whole mass of oxygen, not just the 16, right? It's got to be the 16 times 3, which is the 48. So it'll be the 48, the part, divided by the whole, which is 106, times 100. So I can guess it's going to be around 50%, right? So 48 divided by 106 equals times 100 is, I'm coming up with, 45 point, we'll call it 28%, right? Not too bad. The biggest thing you got to remember is what we did here with the highlighter, all this stuff, that it's the total mass of the element, not just the single mass. It's however much of the total element is there. From there, we took one step further into, I think, 9.7. I'm going to take a look here. No, 9.5. I'm way off. 9.5, which was percent composition by mass of hydrated compounds. Now, this one was a little bit more complicated because we have this water here. But the trick with this is, if you remember, water weighs 18. Right? That was the little trick that we pulled with this. So if I want to get the mass of this, it's going to be the mass of magnesium plus the mass of sulfur plus the mass of oxygen times 4, because there's, oh, my pen turned off. Hang on just a second. There we go. Oxygen times 4, because there's 4 oxygens. Now, I know this multiplication symbol here, that means multiply in math class, but we said you're going to keep adding here. And the trick, I think anyway, is if you keep water as one whole thing, and in this case, multiply by 7, because there's 7 waters. Because what I can do now is find my periodic table and say, okay, magnesium weighs 24, so we'll substitute that in. Sulfur, I think, is 32. Yep, 32, plus oxygen is 16 times 4, plus we just said water weighs 18. So 18 times 7. And if I start doing the math here, we'll get 24 plus 32 plus, I think 16 times 4 is 64. Yep. 64 plus 18 times 7, I have no idea. 126. And see, the nice part is, since up here, there we go, I want the percent mass of water, I now know the mass of water. I just got to figure out the mass of the entire thing. So let's see here. We'll clean this up a little bit. We'll do 126 plus 64 plus 32 plus 24 is, I got 246. So there's my total. So to do the percent composition of water, it's just going to be the part, 126, divided by the whole, 246, times 100. So 126 divided by 246 equals, I got about 50, we'll call it 1.2%, right? So not too bad. The big trick with this one is that you want, there we go, is that you want to make sure, I don't know, what is the big trick with this one? I guess you want to make sure that you're looking at water and maybe keep water separate. And even though that dot means to multiply in math class, here you want to keep adding through. But otherwise, there's no real tricks to that one. From there, the two big things that we talked about were empirical formulas and molecular formulas and how to figure out both of those. So the difference between an empirical formula and a molecular formula is that the molecular formula tells you exactly what's there and how many of each thing are there. The empirical formula is that same ratio, but is the simplest whole number ratio. So some of you said it's reduced, right? It's just another plug. It's no big deal. But it's reduced as far as you can go. So let's take a look. I got a couple one problem here for you anyway. It wants to know, what is the empirical formula for a compound with a molecular formula of C10, now let's clean that up, 10 H22O4. So I want to see if I can reduce that. And it's not just reducing it, it's reducing it as far as it can possibly go. Well, I think in this case, the only thing I can do is divide the whole thing by 2. So it'd be C5H11O2, right? Because that's as far as it can go. But that would be your empirical formula, because you can't reduce it any farther than that, right? Not too bad. Where it got a little weird was here when you were trying to determine the empirical formula. There were basically, I think, 4 steps that we did. And the first was to convert these percentages that they gave you, right? Here, we'll even do this in color here, and pink, why not? There. Convert those to grams. So the way you do that is just change it to a gram, because you can assume that you have a 100-gram sample total, because it doesn't matter how big the sample is. A percent's a percent. So I can say, okay, I got 64.8 grams of carbon, and then I have 13.62 grams of oxygen, and oh, sorry, that's hydrogen. Boop. No, there we go. Hydrogen, and 21.58 grams of oxygen. And the next thing we wanted to do was to convert that into moles. So that's not too bad. We did that back earlier in this podcast. I'm just going to say, oh, wow, I cannot write. Let me try and put this down flat, see if that helps. Probably not. Nope. So I'll just pack that in there. There we go. Okay. So I know that 1 mole of carbon weighs 12 grams. So let's see if we do, and I hope these numbers work out because I just kind of made them up on the fly. But 64.8 divided by 12 is 5.4, and that would now be moles of carbon. And hydrogen has a mass of 1 mole of hydrogen is 1 gram of hydrogen. So that math is easy. 13.62 moles of hydrogen. And last but not least, oxygen. 1 mole of oxygen is 16 grams of oxygen. So 21.58 divided by 16 is 1.34875, and that's moles. Oh, There we go. And what we do next, let's switch up some ink here, is we write the formula, right? CHO with these numbers as the subscripts. So 5.4, 13.62, and 1.34875. So what I'm trying to do is come up with the empirical formula, which is the simplest whole number ratio. And the smallest number you can have in that formula would be 1. So to accomplish that, what I'm going to do here is divide all of these by whichever one is the smallest. In this case, the 1.34, blah, 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 blah. 1.34, blah, blah, blah. 1.34, blah, blah, blah. Because what that guarantees is when I rewrite this, the smallest number I'll have is 1, because I'm dividing all of them by the smallest. So let's see, 5.4 divided by 1.34875 is, cool, 4.00370. Pretty darn close. You can do the math, but it is pretty darn close to 4. H, right? If I do 13.62 divided by 1.34875, I'm coming up with a number that is pretty darn close to 10. And then O, well, that's going to be 1. So C4H10O. That is my empirical formula. So I can't really zoom out too much more, but what you're doing here, and the hardest thing about this is just remembering what order to do things in. It's not really that complicated. But the first thing I did here was convert those numbers into grams by just switching the units. The second step was to convert from grams into moles. The third step was to write the formula with the moles as subscripts. Fourth step was to divide them all by the the smallest. And then the fifth step is just round as needed. So cool. Where we took it from there, the last thing we did before we left was the molecular formula. And it says, so based on the formula above, what's the molecular formula for this compound if the gram formula mass is 74.14 grams per mole? So there's a couple different ways you could do this, right? We know it's C4H10O. So we could say, okay, possibilities. C4H10O1. Or we could do C8H20O2, or we could do, let's see, if we go by 3, that'd be what, C12H30O3, C16H40O4. Basically, I'm just doing, times 2, times 3, times 4, because that's all molecular formulas are, is they're just a multiplied up version of the empirical formula. So this is what I call guess and check. And you could do guess and check and see, which one of these adds up to that 74.14 that you need. And that's fine. It's just going to take a little while. A faster way to do it, and I'm going to delete these just to make my life a little easier and save me some space. A faster way, I think, is to figure out what the mass of this is. So let's see, I'm going to have carbon, which is 12 times 4, and that's going to be what, 48, right? Plus hydrogen is 1, and there's 10 of them, so times 10 is 10, plus oxygen is 16, so 16. So we got 48 plus 10 plus 16. Let's see. Whoa, wrong buttons. 48 plus 10 plus 16 is 74. So what that means is that this thing weighs 74 grams, which is pretty much what I need. So that means that is the molecular formula. Well, that was a lot easier than I wanted it to be. So let's just change this because I can do that. Let's pretend this doesn't say 74. Let's pretend it says, let's do that. Oh, let's say it weighs 370. Woo! Okay. So like I said, you could figure out which one of those formulas before added up to 370. But the easier way, I think, to do it, and I'll try and keep with colors here, is take the 74 that you knew right here and divide that by the 370 that you knew right there. And when you do that, you should get, because I just did it, 5. Okay. So what that tells you is that you have to take your empirical formula mass and multiply by 5 to get the mass you want. So to figure out the answer, take your empirical formula, C4H10O1, and multiply that, in this case, by 5. And you'll get what? C20H50O5. Whoa, sorry. And that is your final answer. So, and if you don't believe me, you can do the math and check, and guess what? It's going to add up to 370. Why? Because I'm right. That's why. And not only that, but because, yeah, I'm number one. That actually has absolutely nothing to do with it. But it really does work out. And that's what's going on. So that was all of Unit 9, believe it or not, in a nutshell. So with that, I'm going to wrap this up, but let's just recap what we talked about. So Unit 9 was all about the mole, right? A mole is 6.02 times 10 to the 23rd particles. 1 mole always has a specific mass that you can find on your periodic table. Rounded to the nearest whole number is fine. What else? Oh, 1 mole of a gas always occupies 22.4 liters of space. So there you have it. And then from there, we talked about converting from moles to grams or moles to particles or moles to liters or anything in between there with unit cancellation, which was those homeworks. I want to say it was like 3, 4, 5, and 6 were the ones that were all about that. And again, this is all in the Unit 9 folder on Google Drive or the Unit 9 playlist on YouTube, so you can check out those videos. Then we talked about percent composition. The formula is on the back of your reference table. Not too bad. You can either do it for a regular compound or a hydrated compound, which, by the way, heads up, your hydrated compounds lab is due the Friday we get back. So don't forget about that. That's kind of important. Also, as a little heads up, let's see, what do I got? Oh, 6 weeks ends Tuesday. That's bonkers. 6 weeks ends Tuesday, and then the marking period, the second marking period, ends the last day in January, the 30th. That is cocoa nuts. But anyway, I digress. What was I saying? Oh, so that was percent composition. Then we talked about empirical and molecular formulas. The empirical formula is just reduced to the lowest whole number ratio. And we determined empirical formulas and molecular formulas. So that's everything. We'll have some problems to look at tomorrow, kind of to help review in case you didn't catch this video. But if you did, it's definitely going to get things flowing and you'll get more out of tomorrow. So I hope this helped. I hope you had a great winter break. I can hear, I don't know if my daughter is laughing or crying upstairs. So I'm going to go and make sure she's doing okay. Des is with her. It's fine. It's not like I just left her up there. But hope you had a great break. I will see you all tomorrow. Thanks for watching. If you have any questions, feel free to tweet me or you can email me. You all should have my email at this point. So with that, I am out of here.